Now, the deuterium diffuses into the lattice, and evidence shows that it does so in a much more shallow potential well structure. The electron actually enters the band structure of the metal, and we know this because you see deuterium migrate in the lattice when you put an electric field. If you have an external experiment where you put an electric field across that lattice, you will actually observe that D+ migrates through the lattice. I'll mention more on that in just a moment. Okay, then the next slide is, again, see, next one. I think we're going the wrong way again. Thanks. Again, as Professor Yeager mentioned, the energetics may be calculated something like this. The electrochemical potential between the surface and the lattice must be continuous across the interface. Therefore, the chemical potential, which is added, or the electrochemical potential is then may be broken down into the chemical potential, and a solution potential term when multiplied by the Faraday gives you a chemical potential term, and that must be the same in the lattice. We can measure the difference in the solution and the galvanic potential quite easily by a number of ways. It's first done by Frumkin, and this can range from values around 0.8 electron volts. Some reports claim that it is as high as 2 electron volts. So we say, wonderful, that's not very much, but as Professor Yeager pointed out on the next slide, if you were to try to accomplish the same 0.8 electron volt chemical potential by compression of hydrogen in a very simple gas phase reaction, you would have to attain, indeed, astronomical pressures. So the point is that although these pressures are certainly not maintained in the lattice, they're not developed in the lattice, the cohesive strength of palladium is on the order of 4,000 atmospheres, the process of dissolution of deuterium into the lattice by whatever process is going on here, and it's very strange that this whole phenomenon of hydrogen dissolution into a lattice giving up its electron is indeed strange. That whole process must be a very high energy process. We also note that D2 is never observed in the lattice. Deuterium gas is never observed in the lattice, which also indicates that there is very little s electron character surrounding this deuteron. So that in itself is an important observation. The deuteron must be shielded and is indeed existent in the lattice as D+. And a further important piece of evidence or hint as to what's going on is that high constant separation factors between hydrogen and deuterium, the relative ratios of these materials present in the lattice. If you measure separation factors for electrolysis of hydrogen and deuterium in the aqueous portion, you can accurately predict what it is by standard statistical mechanical means, and it fits the theory exactly by any measure. If, however, you measure the separation factors in the lattice, then you find that you get extremely high and abnormally high separation factors for hydrogen versus deuterium in the lattice, and this can only be explained by statistical mechanical models if you assume that the particles are in there as classical oscillators, not as quantum oscillators, but as classical oscillators. In other words, they are in flat potential wells, extremely low potential wells. It appears as though the interactions between these particles may require much less energy than we would think by normal Coulombic propulsion considerations. So in the end, we have high compression or equivalent high compression in the lattice. We have extremely high mobility in the lattice. We have many collisions, and we have long confinement times. So next slide, please. So then we have to consider then under these high energy conditions whether we can indeed induce reactions of this form in the lattice. And our evidence has been measurements of neutron flux from this electrode, mass spectroscopic results, although they are quite ambiguous in the cases, in the experiments we have done, except for mass equals 1, which is of little interest right now. Gammas associated with an N-gamma reaction, which I'll show in just a moment. Tritium accumulation measurements in the liquid, and calorimetric results. Next slide. Just skip that one, go to the next one, please. Next slide. Next slide again. One way to measure tritium is to use a seal cell. We would seal this up maybe in a nickel cell, and we have designed and built a couple of these now, and then obtain the tritium, recombine the tritium with a catalytic heater. That's what this device would here, or a catalyst. Recombine that so that you form T2O in the cell, or TDO, and then let that accumulate. This would be a method for doing that. However, in the present measurements we've done, we have just allowed the tritium formed in the lattice to exchange with the deuterium atoms on the surface at equilibrium, and that then, of course, will exchange with the water, and you get TDO liquid in the aqueous phase. The next slide shows a spectrum then obtained of the aqueous portion with a scintillation counter. This is a beta ray spectrum, which grows in times predicted by considering a differential equation which describes the fraction of tritium accumulation in the dewar as a function of the initial concentration. The sampling frequency, you have to take a sample every so often. The total number of atoms of deuterium to begin with in the cell, the deuterium-tritium separation factors, the rate of the nuclear reaction, and the rate of electrolysis. And it fits the theory then quite well. The growth in, or the fraction that we find in that is a function in the cell as a function of time. The next slide shows the reaction, or the gamma ray spectrum of the in-gamma reaction, a thermal neutron reaction with water in the surrounding water bath. We place a lithium or a sodium iodide detector at the Fermi length, which is the distance that you expect total thermalization of the neutron coming out of the cells, thermalized by water in about 6 inches. A 2.45 million electron volt neutron is. We then measure the gamma ray spectrum, and we get a spectrum that looks like this. And if we turn the cell off, or we make the measurements elsewhere in the laboratory, we do not get this peak. This is expected. This is the expected peak for an in-gamma reaction with hydrogen.